In mathematics, the viscosity solution concept was introduced in the early 1980s by Pierre-Louis Lyons and Michael G.Crandall as a generalization of the classical concept of what is meant by a solution to a partial differential equation. It has been found that the viscosity solution is the natural solution concept to use in many applications of PDEs, including, for example, first-order equations arising in optimal control, differential games or front evolution problems, as well as second-order equations such as the ones arising in stochastic optimal control or stochastic differential games. The classical concept was that a PDE over a domain has a solution if we can find a function u continuous and differentiable over the entire domain, such that satisfy the above equation at every point. If a scalar equation is degenerate elliptic, one can define a type of weak solution called viscosity solution. Under the viscosity solution concept, u need not be everywhere differentiable. There may be points where either or does not exist and yet u satisfies the equation in an appropriate generalized sense. The definition allows only for certain kind of singularities, so that existence, uniqueness, and stability under uniform limits hold for a large class of equations. Definition. There are several equivalent ways to phrase the definition of viscosity solutions. See for example the Section 2.4 of Fleming and Soner's book or the definition using semi-jets in the user's guide. An equation in a domain is defined to be degenerate elliptic if for any two symmetric matrices and such that is positive definite, and any values of and we have the inequality. For example, is degenerate elliptic. Any first-order equation is degenerate elliptic. An upper semi-continuous function n is defined to be a subsolution of a degenerate elliptic equation in the viscosity sense if for any point on any function such that an inner neighborhood of we have a lower semi-continuous function n is defined to be a supersolution of a degenerate elliptic equation in the viscosity sense if for any point on any function such that an inner neighborhood of we have a continuous function u is a viscosity solution of the PDE if it is both a viscosity supersolution and a viscosity subsolution. Basic properties. The three basic properties of viscosity solutions are existence, uniqueness and stability. The uniqueness of solutions requires some extra structural assumptions on the equation, yet it can be shown for a very large class of degenerate elliptic equations. It is a direct consequence of the comparison principle. Some simple examples where comparison principle holds are, with H uniformly continuous in X, so that is Lipschitz with respect to all variables and for every n, for some. The existence of solutions holds in all cases where the comparison principle holds and the boundary conditions can be enforced in some way. For first-order equations, it can be obtained using the vanishing viscosity method or for most equations using Perron's method. There is a generalized notion of boundary condition in the viscosity sense. The solution to a boundary problem with generalized boundary conditions is solvable whenever the comparison principle holds. The stability of solutions in holds as follows. A locally uniform limit of a sequence of solutions is a solution. More generally, the notion of viscosity sub and supersolution is also conserved by half-relaxed limits. History. The term viscosity solutions first appear in the work of Michael G.Crandall and Pierre-Louis Lyons in 1983 regarding the Hamilton-Jacobi equation. The name is justified by the fact that the existence of solutions was obtained by the vanishing viscosity method. The definition of solution had actually been given earlier by Lawrence Evans in 1980. Subsequently, the definition and properties of viscosity solutions for the Hamilton-Jacobi equation were refined in a joint work by Crandall, Evans and Lyons in 1984. For a few years the work on viscosity solutions concentrated on first-order equations because it was not known whether second-order elliptic equations would have a unique viscosity solution except in very particular cases. The breakthrough result came with the method introduced by Robert Jensen in 1988 to prove the comparison principle using a regularized approximation of the solution which has a second derivative almost everywhere. In subsequent years, the concept of viscosity solution has become increasingly prevalent in analysis of degenerate elliptic PDE. Based on their stability properties, Bals and Suganidis obtained a very simple and general proof of convergence of finite difference schemes. Further regularity properties of viscosity solutions were obtained, especially in the uniformly elliptic case with the work of Louis Caffarelli. Viscosity solutions have become a central concept in the study of elliptic PDE, as can be corroborated by the fact that currently the user's guide has more than 800 citations, being the most cited paper of mathematics for 6 years straight from 2003 to 2008 according to Mathstia.net. In the modern approach, the existence of solutions is obtained most often through the Perron method. The vanishing viscosity method is not practical for second-order equations in general, since the addition of artificial viscosity does not guarantee the existence of a classical solution. Moreover, the definition of viscosity solutions does not involve any viscosity of any kind. The theory of viscosity solutions is completely unrelated to viscous fluids. Thus, it has been suggested that the name viscosity solution does not represent the concept appropriately. Yet, the name persists because of the history of the subject. Other names that were suggested were Crandall-Lyons solutions, in honor to their pioneers, weak solutions, referring to their stability properties, or comparison solutions, referring to their most characteristic property.